Hello friends, welcome to C Field Academy again, where we learn together from each other. I am Suraj, and today we are going to discuss an important topic from operating systems, which is the CPU scheduling algorithms. So let's get started. So we are going to cover these topics today. To start with, we will start with the introduction to CPU scheduling and some very basic concepts related to CPU scheduling, like CPU burst, IO burst, and what is the definition of CPU scheduling, what it really means, and then we will see the function of scheduler, dispatcher, and so on. And once we are done with the basic concepts, we will then go to some of the important criteria that is used for CPU scheduling in terms of performance, in terms of statistics, and so we will just discuss some important criteria of CPU scheduling. Then we will move on to see what are the popular or important CPU scheduling algorithms, and then we will just see a small one-liner description of each of them, and we will see if they are preemptive or not. So just a basic comparison of these algorithms, and after that we will go to each algorithm and one by one and cover its basic overview, cover the basic definition, and we will also see a short example for each of them. So the first one we will cover is the first come first serve algorithm, which is probably the simplest algorithm that I know of, and it's pretty intuitive as well. Next we will go to a little more variant of CPU scheduling algorithm, which is the shortest job next. Sometimes this is also called a shortest next burst algorithm, and then we will go to the another simpler algorithm similar to FCFS, which is the round robin scheduling. After that we will move on to a bit different context in terms of giving importance to various processes. So we will cover priority scheduling. Then we will move on to a little more complex scheduling algorithm, which is the multi-level queue scheduling. We will see how it's different from the other algorithms, and finally we will go to the most complex one, but then the performance or from the various criteria, this is probably the best one, which you know covers which solves the issues that are seen in the previous simpler algorithms. And finally we will cover finally there will be a few review questions which you can look at to solve if you wish to, and I'll make sure to respond back to your comments if you post them under the same video. So first things first, some very basic things. First thing is, in the context of CPU scheduling, we generally don't differentiate between processes or threads, which means these algorithms are simply applicable for processes. So we will use processes in this whole video, but in terms of threads also, sometimes we may talk about same algorithms for thread. So we are necessarily not differentiating between threads and processes in this video. The next important thing is, when we say CPU scheduling, we are considering the most simplest mechanism of a computer, which means there is a single processor or a single core processor, single core processor on a computer, and that's what is to be basically shared across programs or processes. When it comes to multi-processors or multi-threaded processors or multi-core processors, these algorithms may not be directly applicable, and they may have to be adapted a little bit to make them apply on them. The next important point is, so these algorithms or the entire video, I would say, is a skimmed summary from the book Operating System Concepts by Silver Scratch, Galvin and Gagne. So So if you want to go and understand any specific topic in detail, please I would recommend you to go to the book and see chapter 5, CPU scheduling for 10th edition. So for different editions, the book the chapter might vary slightly, but as such you can just look for the chapter CPU scheduling out there, and you can get all the details from the book. So this is one of the pretty vastly used undergraduate texts. Even I had used it during my undergraduate study, and it's definitely a very good book. I would say I would highly recommend to you. The next item is so we'll cover each of these algorithms one by one, but we won't go into detailed problem solving. We will see very short example of each of these algorithms, which will make the concept clearer, but we won't go to any specific or a detailed problem solving. So I have I have noted down that I'll create separate videos for each of these problem solving. So if you wish to go into detailed problem solving, I'll definitely make sure to link those videos here, and you can go and watch those videos. So let's get started then. So first of all, some very basic introduction and to concepts. The first thing is, what is CPU scheduling? So CPU is, if you would have seen my previous videos or know some basics of operating systems, so CPU is nothing but a resource. So it's a resource of a computer, and that resource has to be used by multiple processes that are running. So there may be multiple processes, and they might want to use the CPU, and hence CPU has to be shared across those processes. And every process that uses CPU does some work or some meaningful work. So CPU scheduling is nothing but a procedure of assigning CPU to a process that is running and doing some meaningful work. And in fact, it is one of the very basic fundamental operating system functions, because CPU is a very important resource. It's probably the most important resource on the computer that operating system has, and that all processes compete for. So next, CPU I/O burst cycle. So it has been seen that when processes run, they are either in two modes. One mode where they are using CPU and then doing some important work or meaningful work. The other mode is when they are not using CPU, but they are waiting for an I/O operation, or they are doing some I/O operation to complete. And when they are doing the I/O operation, the CPU can actually be released and then assigned to another process. And hence what we say, that in general process execution or in its lifetime, when a process executes, it alternates between CPU cycle and I/O cycle, or CPU execution and I/O burst. So here is a pictorial representation of how it looks like. So when a process executes, it might have a first CPU burst, and then it will release the CPU and then use the I/O. So at this time, processor can be assigned to CPU can be assigned to a different process, and the sizes of CPU and I/O burst might also vary. Now this one is a slightly longer CPU burst, and that way, and then what you can see is process generally alternates between CPU bursts and I/O bursts. And it has been noted by observing various operating systems that usually there are a large number of CPU bursts and a small number of large number of small CPU bursts and small number of large CPU bursts. And next, now we have discussed CPU I/O bursts. So next, the process of scheduling. So who actually schedules? Who is responsible for scheduling? Who does the job of assigning the CPU to a process? So there is a component called as a CPU scheduler, which actually does this job. So it will look for processes in the ready queue which is present, and look and find and select one process based on certain strategy, and then assign CPU to it. So CPU scheduler is a component that does the scheduling assignment. So next, we have to know what is preemptive and non-preemptive scheduling. So there are times when a process is using a CPU and it is using for a long time, but the CPU is, and once the process completes, the process will then release the CPU. So when the release of CPU is done voluntarily or done or completely given to the process, then we say that CPU scheduling is is non-preemptive. So non-preemptive means if the process once given a CPU, it keeps it until it terminates or until it goes to the IO cycle and then releases the CPU. So nobody else has the authority to take away the CPU from the process. This is called as non-preemptive scheduling. So it's only the process that can voluntarily release the CPU. Whereas if another component or the CPU can be taken away from the process and given to some other process, we say that the process is preemptive scheduling. And as you may guess, mostly all OSs use preemptive scheduling, because in every OS there are priority, high priority and low priority process, and we always want high priority process to take over the CPU even though some low priority process is running. So what we want is the low priority process to save its state and then the CPU be assigned to a high priority process, and this is preemptive scheduling, and most OSs use this scheduling. Lastly, another important component is the dispatcher. So dispatcher is the component or the module that actually gives the control of CPU to the new process selected by scheduler. So once the scheduler selects the process, it's the dispatcher who will actually do the assignment of the CPU, and it does it using certain steps. Now dispatcher also takes care of switching context between one process to other. So here is an example, because when the CPU is switched from one process to other, we have to save the state of the previous process that is executing. So let's say we have processes P0 and P1, and P1 is currently executing on the CPU, and we want to switch from P0 to P1 because P1 is a higher priority process and this is a preemptive scheduling. So the dispatcher, what it will do is, before it executes P1, it will inform P0, boss, now please save your state because I have a higher priority process P1 that is going to be executed. And what it will do is it will take all this temporary state of P0, which means the current location where it was running and other stack register values, and it will save to a special area which is called as PCB0, so that the process can be resumed later when it will get the CPU. And once it saves the state to PCB, now it goes to P1's PCB, which means P1's program location and its stack and other temporary variables, and it will restore back to the current state, and it will assign CPU to P1. So this is what happens when a context switch happens between process P0 to P1, and this is done by the dispatcher. So dispatcher does context switch. Dispatcher also makes sure that that the program's proper location is resumed. So when it was when the program starts or the process starts, we have to make sure how much it had already run, that is not repeated, and only from this new line from which it has to be executed needs to be run. So this is done by dispatcher. And also remember, we already discussed the context switch can be voluntary and non-voluntary. So if it's preemptive scheduling, then only the context switch happens using the dispatcher. Otherwise only when the process releases, that is when then, which means it is through, I mean, non-voluntary is actually pre uh, preemptive, and voluntary means it's non-preemptive. So non-voluntary can happen through the dispatcher, which means dispatcher has the authority to remove or take away CPU from P0. Otherwise only when P0 exits or P0 goes to IO, the context switch can happen. Alright, so I hope the basic concepts were pretty clear to understand. Now let's move on to the various criteria or various scheduling criteria that are used for CPU scheduling. So the first important criteria is CPU utilization. So this is nothing but a measure of how much time CPU is actually getting utilized as compared to CPU is not doing any work. And ideally what we want the CPU utilization to be as high as possible, because that's what we want. I mean, that's when we say that we are doing real work. We always want higher CPU utilization, and generally this ideal range is from 40% to 90%. 90% is when CPU utilization is very high, and 40% is fair amount of CPU utilization. The next important criteria is throughput. So we always want the number of processes to be as high as possible. So we cover as many, we execute as many processes as possible as quickly as possible. So throughput is just a measure of number of processes that are completed per unit time. Next important criteria is the turnaround time. So generally when processes come and they want to get executed, one thing to note is every process is, we have to see that how much time does it take for the process to get completed. It's an important criteria because we don't want processes to wait for a long time and then get executed over the CPU. So total turnaround time is basically the time when the process actually gets started, which means actually is submitted to the ready queue, to the actual time of completion. So when the last execution is done for the process, and in between the process may switch from ready state to waiting state for a number of times. It might be waiting to get the CPU for various reasons, because of the CPU scheduling algorithm or whatever, but the turnaround time is the starting time to the end time. Another important criteria is the waiting time. So we generally always want the waiting time to be minimized, because that is a waste time for the process. So this is nothing but the total amount of time spent waiting in the ready queue. Now it might be during the start that the process is waiting to get executed, or it's possible that it has been preempted, or CPU has been taken away from the process and it is waiting. So it's the sum of all the time the process spent waiting. Another important criteria or important criteria of scheduling is the response time. So which means how much time it actually took for the process to start its first line of execution. So basically from the time the process arrived to the ready queue to the first time it is scheduled on the CPU, or the first response is produced. This is also an important point at time, because we want to reduce response time as less as possible. And it is and basically it is part of the waiting time, if you notice, which is the first time the process spends waiting in the queue. And generally, as we have already discussed, it's always desirable to maximize CPU utilization, throughput, whereas minimize the waiting different times, that is turnaround time, waiting time, and response time. Alright, cool. So let's move ahead and see the different popular or important algorithms that we have for CPU scheduling, and let's go through them and compare to each other a little bit. So here are all the algorithms that we have. In fact, we have 6 algorithms. The first one is the first come first serve. So it's the simplest algorithm, which just takes care, or which takes the simplest algorithm, which is in the queue. So it just assigns whichever process came early will be assigned the CPU first. So there is no complicated logic in it. And this process and this is not preemptive, so which means once CPU has been assigned to the process, it can only be voluntarily taken, it can only be voluntarily released by the process. So there is no way that CPU can be taken away from the process. The next one is the shortest job first. So there are scenarios where, if the job is long enough, or we don't want other small processes to wait, because those small processes will wait for a very long time, and this will only increase the total waiting time. So this algorithm sees what is the size of the next CPU burst, so which means what is the next amount of time a process will take when it runs the CPU, and based on that, based on the size of the next CPU burst, it will assign CPU to the smallest burst, to the process that has the smallest burst. And this algorithm comes in 2 flavors, which means it can be preemptive and non-preemptive. When it is preemptive, then we say that it is the shortest next CPU burst, as simple. And when it is non-preemptive, that is when CPU can be actually taken away by the dispatcher. So what happens in non-preemptive is, whenever a process is running, the running process on the CPU, if its CPU burst is longer than any new process that has come, that process may be preemptive by the dispatcher. And the new process with the smallest CPU burst will be executed. Alright, so next move on to the next simple algorithm is round robin. Now in round robin's algorithm, what happens is there is a time slice. So regardless of the process and the length of the process, there is only a specific time slice that is assigned to each process, and then the next process is picked, and the process that was preempted, that process is now actually given back to, or put in the ready queue, and it will be, and the next processes. So this is an algorithm which is kind of a fair, and it compared to the FCFS. Next one is the priority scheduling. So this is round robin scheduling is preemptive. Next is the priority scheduling. So since the operating system has a lot of processes, and there may be some processes that are important, whereas others that are not important, even though they may be longer, we want the higher priority task to run on the CPU. And this algorithm uses a priority number, and prioritizes important processes, and only runs the important processes first, and then only runs the non-priority processes. And as you can guess, so this is non-preemptive, which means once the priority process takes over, it takes over till it completes the CPU, or it goes into IO. So the next one is the multi-level queue. In fact, this is a combination of priority and RR, which means it takes care of priority scheduling, whereas it also uses a time slice to actually schedule the CPU. And as we will see shortly when we will go through it, what it does is it first executes the priority process, and those priority processes are kept in different priority queue, and within that queue these processes are then run using a time round robin scheduling based on a time slice, and this is a preemptive algorithm. Lastly, the multi-level feedback queue, which is probably the most complex. So it is similar to multi-level queue, but it is a little bit fairer than that because it uses some complex strategies to remove the processes from the and it moves certain processes between the priority queues, and it reduces the higher priorities and higher priority processes, and sometimes it may increase the priority of low priority processes to just ensure the overall scheduling is fairer. Alright, cool. So let's now go ahead and see each of these algorithms one by one. So one important thing is don't worry about each of these algorithms or problem solving for each of these algorithms. We will make sure to cover them as separate videos, and we will link them here so that you can easily go there and then look at the problems on each of these algorithms. Alright, so let's start with the first algorithm. So the first algorithm is first comes first serve, the simplest of all. So whichever process came first will be assigned the CPU first. It's the simplest strategy, and it's also pretty easy to implement. We don't need a queue, we just have a ready queue, and we will have times when these processes came, and we can just use that to see which process came early and assign CPU to it. It's a non-preemptive algorithm, so which means CPU once allocated to the process will only be released by the process when the process is going for IO or when it finishes. But there are issues with this, as we will see shortly, is that since this is a very simple algorithm which doesn't take care of how long the process will take the CPU, the average waiting time is not minimal. So here is an example of first come first serve process. So let's say we have three processes, P1 to P3, and they arrive in this order. So P1 comes first at time 0, P3 comes next at time 1, P2 comes third at time 2, and each of those burst time, which means P1 takes 20 seconds to execute, needs 20 seconds, P2 needs 5 seconds to execute, and P3 needs 7 seconds to execute. Now using this algorithm, this is how the scheduling will occur. So at time 0, because P1 came early, first we will assign P0 the CPU. So P0 will take the CPU, and P0 will get executed till time t equals to 20, which means till 20 seconds, and then only the CPU will be released. And at that time we will see that P3 is the next one which came early because it came at time 1. So we'll execute P3, so that will take 7 times 7 seconds, and once CPU is released at 27 second, P2 is executed. So notice what happens. Even though P3 and P2 were very smaller, they were of 5 and 7 sizes, still we assigned CPU to P1, and P3 and P2, they were made to wait a long time. And in fact, notice what happens here is P1 didn't have to wait, so wait time for P1 is 0. P3 waited till 20 and it came at 1, so its waiting time is 19. P2's waiting time is, because it came at 2, is actually 25. So notice the total waiting time is 19 plus 25, which is around 44. And if we calculate the average waiting time, so average waiting time is around 50 seconds. This is close to 15 seconds, which probably is not good. And in fact, we want the waiting time should be as less as possible. If we had scheduled it slightly different, we would have seen a lower waiting time. So that's probably an important point here. Average waiting time is not minimum. And what happens is, if a large CPU bound process comes and it holds the CPU for an extended period of time, it causes other processes that to wait, even though they are IO bound jobs and they only need small amount of CPU. So they will have to wait for a very long time. So an example of this in real time is, let's say you want to make a copy of the book, or you want to get a book photocopied. Let's say a guy wants to get a book photocopied, but that guy reaches the photocopying shop first, whereas you just want to photocopy a couple of pages, but because you reach it there late, you will have to wait for that guy to complete the whole photocopy of the book, and you'll have to wait a very long time until that that guy's photocopying job is done. So this is a demerit, and hence comes the next strategy, which is the shortest job first. So shortest job first checks the size of the job, or what is the amount of time the job is going to get executed before it actually allocates CPU. So this is a prerequisite. In fact, a process has to declare its length of the next CPU burst, so how long the process will take on the CPU, and based on that, what the dispatcher does is, or scheduler does is, it sees whichever CPU has the next smallest CPU burst, CPU is assigned to it. And if there are multiple jobs that have the same next burst, it will use FCFS, which means the process that came first, to break ties. And as we can see, this shortest job first can be a preemptive or a non-preemptive. So it's preemptive when a running job, current running job, can be when CPU can be taken away from the current running job. So let's say a job is running on the CPU, but there is a new job that comes that has very less next CPU burst. So the dispatcher can now context switch or remove the job running on the CPU and assign the new process the CPU. So this happens when it's preemptive. If it's non-preemptive, then the running job is not interrupted. The shortest job first will only compare the waiting job's next burst cycle. And as you might have already guessed, the average waiting time here is better compared to FCFS. So let's see an example. In fact, it's the similar example. So we have three processes. In fact, they all arrive at the same time, 0 0 0 0, and P1 is the longest. It has 20 seconds of running time. P2 has 5 and P3 has 7. So in this case, what the dispatch scheduler will do is, because P2 is the smallest with 5 next burst size, so P2 will be assigned the CPU, and only after the end of 5th second P2 will release the CPU, and then the next one, which is P3, which has size 7, will be executed on the CPU, and the longest one, which is P1, is executed last. And let's compare the waiting time in this case. So if you see the waiting time in this case, P3 had to wait just 5 seconds and P1 had to wait 12 seconds. So the total is 17, and the average waiting time is 17 by 3, which is about 6 seconds, close to 6 seconds. Compare this with FCFS, where they had the average waiting time was 15 seconds, but the burst time was similar. They was just slightly different with the arrival times, but just see how much better SJF, or shortest job first, is compared to FCFS. But there is a catch here. Now notice, it's practically impossible to implement or know the next CPU burst, because none of the processes know how long they will take when they are given CPU, and hence this is practically impossible. But there are approximations to it, and generally what we approximate is the previous CPU burst. So it's assumed that the previous CPU burst size, so the process will take that much time only on the CPU, and based on that the algorithm is usually implemented. Alright, the next one, which is a variant of the FCFS, is the round robin scheduling. So in round robin scheduling is kind of, we can say it's FCFS with preemption. So what we do is we assign the first process which came first, but we'll only assign for a predefined time slice. So predefined time slice is defined, and once the time slice is over, CPU is taken away from the process, and then the next process is assigned the CPU. So this allows for a bit fairer compared to FCFS. And so there are two cases when CPU can be removed. Either the process completes its execution, or it goes to IO and then it releases the CPU by itself, or its time slice has expired and then the dispatcher actually takes away CPU from it and places the process back to the ready queue. So this is when the CPU burst is longer than the time slice. If CPU burst is less than the time slice, then the process will voluntarily release the CPU, as we discussed. So here is a example of round robin. So let's say we have three processes, P1, P2, P3. They arrive in this order. So P1 arrives first, followed by P2, followed by P2, followed by P3. And P1's burst is 19, P2's burst size is 5, and P3's burst size is 7. So as we can see, because round robin is FCFS, P1 will get executed on the CPU because P1 came first. But our time slice is only 4, which means we will only allow 4 seconds of P1's work to be completed, and then we will put the P1 back to the scheduler queue or ready queue. So what happens is at time t equal to 4, P1 will be removed from the or CPU will be taken away from P2, and its new time will be updated. So which means P1's arrival time will now be updated to 4, and the remaining time that P1 will have is 15. Once that is done, we will again compare and see whose arrival time is less. So in this case, P2 will get a chance. So P2 will get executed on CPU for the next 4 seconds. And notice P2's burst is 5 and it is more than 4, so it will not be able to finish it, and it will have to be release the CPU at time t equal to 8. So once at time t equal to 8, we will place P2 back to the ready queue, and P2's arrival time will now be updated to 8, and the remaining burst size of P2 is now 5 minus 4, which is 1. Lastly, now is the turn of P3, because P3's arrival time is now lower. So P3 will get the CPU, and P3 will get executed for 4 seconds, that is from 8 to 12. And once it reaches 12, P3 has to release the CPU because its time slice has expired. So P3's arrival time will now be updated to 12, and P3's remaining burst time will be updated to 7 minus 4, which is 3. So at time t equals to 12, if you notice, all the processes have taken their time slice once. Now again comes the turn of P1, because P1 has its arrival time less. So P1 gets executed for another 4 seconds from 12 to 16, and once at time t 16, P1 will have to release the CPU, and P1's arrival time will be updated to 16 now, and P1's burst time will also be reduced from 15 to 11, 15 minus 4, and at time t equals to 16, again the turn will come for P2, because P2 now has the lowest arrival time. So P2 will get executed, but P2 only has one burst remaining, so P2 can get completed pretty easily at time t equal to 17. So at time t equal to 17, P1 is now completed, P1 is no longer needed, and at time t equals to 17, again we will see which process arrival time is lower. We will see that it's P3, and P3 will now get executed at time t equals to 17. And notice P3 only needs 3 seconds. So P3 will get finished easily within the time slice, because the time slice is 4. So P3 will be done at time equals to 17 plus 3, which is 20. So P2, P3 is now done, and next comes the chance of P1. In fact, there is no other processes remaining, so it will be always P1 that will run for the next 3 time slices, because the remaining is 11, so it will turn 4, 4, 8, and then 3. So this is the order of how the processes will run. So notice what happened in this case. It took care of advantage of both. First is the process that came early was given the chance to run. Secondly, even though first process was longer, we still it allowed P2 and P3 to complete. So it was fairer compared to FCFS. So yeah, so you can see that it's fairer than FCFS. But if you actually go into more detail, you will see that the average waiting time is still often longer, because what happened is, if you have a very long process like P1 was, even though it came early, it's possible that P1 has to keep waiting till its next time slice and only get completed after a very long time, and sometimes we don't want that to happen. Alright, now let's move on to the next one, which is priority scheduling. So what happens is, sometimes we have processes, there are high priority processes which we need to execute on the CPU, even though there is a process already running or there is a process that came early. So priority scheduling takes into account the priority. So let's say in a system we have some foreground processes and some background processes. Foreground processes are processes that need to be user responsive, because user is interacting. So we want foreground processes to have higher priority than the background processes, which it's okay if those processes run slower and then complete later. So this is what happens in priority scheduling. CPU is allocated to a process with highest priority from the ready queue. So what happens is, every process is given a priority number. So let's say in our example we have 3 processes, P1, P2, P3, and those have burst time of 20, 5, and 7, but P0 has priority 0, P3 has priority 1, P2 has priority 2. Now in this case we are assuming that the lower the priority number, the higher its priority. So what will happen is because P1 has the highest priority, as it has 0, we will ensure that P1 runs first on the CPU, and followed by the next priority, which is P3, followed by P2. So this scheduling doesn't take care of the burst time or the next size of burst, or if the process came first. It will just make sure that the process that has the highest priority gets the CPU first. And in fact, notice in this case the processes were non-preemptive, so which means there was no time slice and it was only released voluntarily by the process. In fact, it can be seen that if the priority is the inverse of the next CPU burst, this scheduling becomes exactly same as SJF scheduling, or shortest job next. So if we know the next burst size, and if we assign priorities as the inverse of the next burst size, then we can say priority scheduling is exactly similar to the shortest job next or shortest job first scheduling. Now this can be preemptive or non-preemptive. The example that we saw here was non-preemptive because CPU was only released by the process after it got completed, but there is also a preemptive variant of it. So in that case, what happens is, if even though a process is running on the CPU, currently running, it can be interrupted by the dispatcher and removed, and a new higher priority process can be scheduled on the CPU. That is when it's preemptive. So yeah, still, even though this is a good approach, it's possible that some low priority process may end up in having indefinite blocking or starvation, because they may never get a chance to run on the CPU because there are always priority process running, and hence this scheduling algorithm is also cannot be directly used by any of the operating systems. And to get rid of these issues that we saw with priority scheduling or with the previous approaches, first come first serve or SJF, there is next scheduling algorithm, which is multi-level queue scheduling. In fact, it takes care of both the advantages of priority scheduling and round robin scheduling. So what it does is for each, so it takes care of, so it assigns the CPU to the processes with higher priority, but then once there is also a separate queue that is maintained for each priority, so that CPU is assigned based on time slice to each of those higher priority processes. So this is what I was saying. So if there are multiple processes in the same priority queue, or if multiple processes are there for the same priority, then round robin scheduling is used with a time slice to switch between those processes. But still, lower priority processes will be in lower priority queues, and lower priority processes will only run when the higher priority queues are completely empty. And so it's a preemptive approach because we use time slicing to share CPU between processes of same priority. So here is an example, as we can see. So let's say we have 5 processes, P1 to P5, and P1 and P4 have priority 0, which means they have the highest priority. P2 and P5 have the third most priority, which is 2, and P3 has the priority 1. So which means these are assigned to 3 different priority queues. Q0 contains P1 and P4, which is highest priority. Q1 contains P3, which is the next priority, and Q2 contains P2 and P5, which is the lowest priority. And notice what will happen is first on the CPU only the highest priority will be executed. So which means P1 will get the CPU first, but P1 will not get it until it's complete. So P1's burst time is 20, but let's say we have a time slice of 4 here in this queue. So P1 will be preempted once the time has reached 4, and the next priority process, which is P4, will run on the CPU, and P4 will run till the next 4 seconds. So P4 will in fact get complete, and then it will be again the turn of P1. So what happens is round robin scheduling is used within processes of the same priority, and processes of the next priority is only executed after higher priority processes are complete. So which means once P1 and P4 are done, that is at the end of 20 plus 3, that is 23, then only P3 will get a chance, and once P3 is complete, then only P2 and P5 will get a chance. So notice what this algorithm enabled us. So it enabled us to share CPU if processes were of the same priority. So it kind of solves the problem of longer job taking the CPU for a longer amount of time. But it still has an issue. What issue? That is, if processes are in the low priority queue, they might have to wait indefinitely. So P2 and P5 in this case will have to wait for a long time to get the CPU, even though they are of lower priority. But if the higher queues, that is Q0 and Q1, is always full, that there are always new processes coming, P2 and P5 may just never get a chance to get the CPU. And hence we come to the last scheduling algorithm, but not the least, probably the most complex, is multi-level feedback queue scheduling. So it is similar to multi-level queue scheduling, but it incorporates additional feedback to make sure that higher priority processes are moved to the lower priority queues if they have received CPU already, and to ensure starvation doesn't occur. So this is how it achieves fairer or removes or reduces starvation. So processes using too much CPU are moved to a lower priority queues. So even though they are at a higher priority, if they are using CPU a lot, they will be moved to the lower priority queues, and this allows processes with lower CPU bursts in a lower priority queue to be executed even though they are at lower priority. Not only that, if it's seen that processes wait for too long in lower priority queue, so they are promoted to higher priority queue to prevent starvation, and it is a preemptive approach. So let's see an example of multi-level feedback queue scheduling. So let's say we have 5 processes, P1 to P5. We have P1 and P4 as the highest priority with 0, P3 as priority 2, P2 and P5 with priority 2, P3 as priority 1. And let's say, so these are in different priority queues, and for each priority queue the time slices are different. For the highest priority, time slice is 8, for Q1 time slice is 16, and for Q2 time slice is 24. So let's see what will happen. As we discussed before, what will happen is time slice for P1 is time slice for Q0 is 8, and Q0 has the highest priority. So first P1 will get executed, and it will take the whole time slice, that is it will take 8 time slice, its burst is 20, and at 8 P1 will end. But then what happens next is, once P1 is completed, P1 will not go back to Q0 because it has already used CPU. We will take P1 and assign to the tail of Q1, so we'll decrease its priority and then assign P1 to the next queue. P1 is here, and then we will go ahead and execute the next process, which is P4. So P4 will get executed next on the CPU, and notice P4 only has 3, so P4 will end at 11, and P4 will get completed. Now what happens is Q0 is now empty. So what this enabled us is to execute processes in the lower priority queue. And not only that, P3 got a higher priority than P1 because P1 has already taken the CPU. So next P3 will be executed, and P3 will now be executed for 8 seconds because P3 has 18 now, which is greater than 8, so it will take 8, so at end of 19. And P1's so let's compute the burst time remaining. For P1, P1 will have 12 remaining here, and sorry, the time slice for Q1 is 16, so this will be actually 16, so 11 plus 16 is 27. So P3 will get completed at 27, and P3 will still have 2 remaining. And then what will happen is the next one will get, P1 will get the next CPU, which has its own next remaining as 12. So this will get 37, 27 plus 12, which is 39. So P1 will take 39. But now notice what happens, because P3 has already got the CPU first, P3 will now be taken and then assigned to the tail of Q2. So P3 will come here. So this will allow processes in lower queues, that is P2 and P5, to get executed, thus preventing their starvation. So now P2, P5 will be executed next. P2 and P5, P2 and P5, and at last P3 will be assigned. So what happened is P1 and P3 were moved to lower priority queue, and this gave a chance for lower priority processes or processes in lower priority queue to get executed. So in fact, this is probably the best scheduling algorithm of all the 6 that we discussed. Alright, so I hope this kind of helped So this kind of helped understanding the various scheduling algorithms, this video. So we are already about to end the video now. So if you want to go into more examples or detailed examples, please refer to my other videos on the channel, and in fact I'll make sure to link them here so that you can have better clarity on each of these algorithms. Cool. So before we end, here are some review questions based on the video today. If you guys need, then you might have to go back to the video and then see different sections of the video to answer this question. So the first question is, in the context of CPU scheduling, define turnaround time and define response time for a process. Next question is, which of the given algorithms will yield in a better response time in general? Is it the first come first serve or the round robin? So in general, which will do better in terms of response time? Please explain why. Next question, under what conditions do you think priority scheduling is exactly similar to shortest job first scheduling? Next, what is preemption? Remember, these were one of the basic concepts that we discussed. And name the scheduling algorithms that are preemptive. Lastly, give an example of issue with multi-level queue scheduling. Discuss how we can resolve the issue, using which approach, and tell us what is the new algorithm that can be used to resolve this issue. Alright, cool. So we have reached the end of the video. Thanks guys for watching. I hope you guys enjoyed the video. If you have any comments, please make sure to put it on the video. If you want me to cover any other topics related to operating system in detail also, you can suggest me. So bye guys, see you again in the next video. If you like, please subscribe and share to my channel. Bye.